My name is Van. I'm coming from the Data Science as a Service team, which is part of Dell IT, previously EMC IT. We're located here in Beersheba. And I'm going to talk today about some experience that our team had with the domain of hardware failure prediction, of course, inside Dell-EMC. So the things that we'll cover today, I will start with a few, really a brief overview of the company and our team structure. Then I'm going to give a short introduction for the domain. The main section of this talk will walk you through a sample use case for hard drive failure prediction that we are dealing with in the last, I think, year and a half. I'm going to talk a bit about a project that we did with data that was collected internally, and then on a research project that we did with open data. I will explain why we did this research. And we'll conclude with some key takeaways, some of them relevant to the domain, some of them are more general, that I think will, hopefully they will benefit all of you. So I guess you heard the name Dell. It's a huge company. Actually, after the merger with EMC last year, it becomes the world's largest privately controlled technology company. It has a huge consumer market, a huge enterprise market. We, as a previously EMC team, are currently more in the domain of the enterprise market. So from all those nice numbers, the most important part for this talk is that Dell-EMC has a huge enterprise install base. Those are storage systems, servers, etc. And this means lots of data that is being collected and sent back home from those systems all around the world. A word about our team. So we have a pretty, I think, unique work model in the environment of the community. We're as a service team, and our organizational from an organization perspective, we belong to the IT department, the IT organization of Dell-EMC. The IT is sometimes captured as the gray, maybe, area of the organization, but the position of our team gives us some very nice privilege that I'm going to talk about at the end of the lecture. As our name suggests, we're as a service team. It means that most of our work is project-oriented. We're doing all kinds of data science related, machine learning related projects to all kinds of mostly internal clients within Dell-EMC. It goes all the way from HR and finance to engineering, IT monitoring, and so on. Recently, we started to offer some of our internal solutions that we developed for internal customers also to external customers. So a word about why are we so interested in the hardware failure domain? Why do we want to put machine learning into this domain? And maybe the two reasons that goes together, the right and the left one, there's I think a new approach for support today in many organizations. Dell-EMC is the one that we're focused in, but I know of many other organizations that goes on the same direction to have the support organization be much more innovative and much more proactive. It means that I will have a model that will give me an alert ahead of time for a predicted failure in one of the critical hardware components on your systems. I will call you, the customer, and I will tell you that I recommend to replace the suspected part in order to avoid the big no-nos of the storage industry, which are data loss or data unavailability, and hopefully we will also improve your experience as our customer. Another important reason that I chose to put in this slide, because it's a really important one, is to prevent over-provisioning, which is a big problem when you fit an equipment to a customer, there's a lot of overshoot for the quality of equipment suited to the specific customer. And by doing smart analytics and monitoring over the use patterns of the specific customer, we can get a much better sense of what are the real needs of this customer and fit him hopefully with a much more accurate set of systems or set of hardware components. For example, for a small business, a mid-range business, probably you won't need the most expensive, most quality 10 writes per day flash drives. You will need only a 0.5 writes per day flash drive. So those are the big three motivations. Inside this domain, you will find many, many interesting questions that we can answer using machine learning, using different techniques from data science. Maybe the two most important ones are the top ones. Wear and tear modeling, I mean, using indicators from the drive or the hardware component, we will predict when this specific component will wear out. The one that we will talk today in the domain of hard drives, but also flash, servers, when they are expected to fail, is it in the next 14 days or a month, depends on the business needs and requirements. Some other interesting question, again, is fitting the right quality of the drive to the customer, and try to answer questions like how probable is that in that customer site we will suffer from a data loss event based on some historical data collected on this customer, other customers on the vertical, other customers that uses this equipment. And there are many more interesting questions here, but you know, we have a limited time, unfortunately. So I will walk you through some project that our team has been dealing with on the last year and a half, and it's specifically aimed to model or predict a failure in a hard drive, which is a huge problem in the storage industry. A word about the starting point in the beginning of this project. So, you know, the industry version of a literature review, we tried to see what was done around academia and industry. It turned out that most of the work in this domain was in the population level. It means that there were very good statistics in terms of annual failure rate, mean time to failure, cross verticals, cross vendors, cross age of drives. I mean, 5-year-old drives will probably have a 15% failure rate and so on. But there was almost no industrial work that tried to predict the specific drive or the specific component failure. There was some academic work on this specific question, but most of it we find it to be too theoretical to be applied into the specific needs and the type of data that our problem that we had to handle in our domain. So at the end, we extracted a very simple question that we wanted to answer here, and this is to develop a classification model that will just give us an alert ahead of time. Once again, depends what the business defines ahead of time, what will serve the business in the best way, for a specific drive failure, and recommend a replacement. Besides, or in addition to the motivations that I already described, one of the main reasons that we got into this use case is the improved logistics. It turns out that one of the most expensive things for the support organization is to send a support engineer into the customer site. And once we have this model, hopefully that can provide us with those predictions, we can tell the support engineer that is going to a scheduled visit on the site that we have those 3 additional drives that we suspect that are going to fail in the next month or so. So please replace those as well. And by that, we won't need an immediate visit of an engineer to a customer site, and we will save lots of money. And of course, this goes well with the general approach of innovative support strategy. Okay, so a few details about the data. So the main technical data in this domain for hard drives is the smart data. This is a standard counters that are supposed to be at least cross in the industry. They are collected by the drive themselves, and they can be extracted from the drive logs. However, they do tend to vary a bit between different vendors. The main challenge, and again, recall that we're in a huge corporation, was found when we really tried to start and look at the organizational data. And we find out that even inside EMC, that had a few different business units that uses hard drives or sells hard drives to customers, find out varied features, varied frequencies in which the data was collected in. There were so many interoperability issues that some of them were untrivial to solve even with the specific domain experts. So you had all kind of different data resources above different platforms, which required to formulate different parsers, to parse the different formats, and to discuss with the SMEs how to understand them. So it wasn't easy at all. And of course, we had all the problems that you probably know from any data set that you get as a raw data. We had sparse tables, missing data, corrupted logs, so on. So lots of challenges in the data here. So much before we got into the modeling, the biggest challenge we had, and this is a challenge that happens a lot in a corporation or in an enterprise environment, is to consolidate the data into one data set that we can use for modeling. Luckily, it was at the time, EMC began to develop the business data lake model. It means that all the organizational data from all business units, from all different types and departments will go into one centralized data set that ourselves as analytics people can approach and hopefully easily access the data and use it for analytics. So what we did, because some specific data set was not ready at the time, is to collect and first identify the right tables from the different business units, from the customer experience department that collected data such as the vertical of the customer, history of use, other systems on the site, etc. Engineering department that had some additional technical information about the data itself, the logs from the business units, the install base with the information for labeling such as failure date if the drive has failed, installation date, age, and so on. So this was really untrivial. And at the end, we got some data set to work with, and we modeled it into a very nice framework that we can then clean and put into a machine learning model, in our case, a random forest classifier. And there was an all modeling process. There is nothing really fancy about it or unusual here. We had intensive feature engineering. We had a lot of iterations with the business in order to optimize the right prediction period. We consolidated all this data into the machine learning model that at the end provided us with a prediction whether this drive will fail or pass or will stay healthy and there's no need to replace it. An important additional output that we got from the model is to use the prediction probability. In our case, it somehow in some level corresponds to the drive failure probability, and to give the business a distribution of the drive failure probabilities across all the population. This really helped the business to decide which is the right threshold in which we set the decision whether we replace the drive or just keep in an open eye as a suspected replacement drive. The real pain point here is that replacing an healthy drive is very expensive and very unhealthy decision in a way, and it costs much more than a potential failure that we missed. So this was a really important output, and you should always be aware that providing distribution of the model confidence can be very helpful to the business. Okay, so I won't get into numbers. I will just say that at the end of this process, results were disappointing, but you know, it wasn't a big surprise for us, okay? The data that we collected was really bad, and you will say, of course, always blame the data. We love to do it. This is a nice privilege for data scientists, right? But in this case, we claimed that the data was really bad. But in that point, we didn't say, okay, so nothing to do here. But we went into research, and the strategy for this research was that we're going to convince the business in the importance of this data collection. I mean, improve your data collection and see what we can achieve. We are going to use open data source, which is much more quality standards, and we're going to hopefully get a better model. Luckily, we had the Backblaze open data. Backblaze is an online backup company that releases for research purposes the data set from all its machines, all of the company's systems, 50,000 different hard drives, different vendors, daily collection, very stable collection, almost no overhead of additional cleaning, so it was a really good, almost instantly go into the model. We could have approached the modeling stage. The most important thing that we did here, and my time is limited, so I will just say a few words, is to incorporate time series-based features. What we did is to take the different counters for each of the drive, feed them with a linear function, and extract some linear features from the function, in addition to some other time series features like mean, median, variability, max diff for those non-accumulative features. And this really made the difference in terms of the model. And this was, we could have done it only because the good quality of the data, which had very stable frequencies. We fed it into, or we approached the modeling a bit differently in that stage. Instead of dividing the trend and the test in the traditional ways using different drives, what we did is, even before we extracted the time series features, we set a border date here, and for the training labeling, we ignored actually everything that is dated to the test period. So even if a drive, even if the data showed us that the drive will fail 2 days after the test period, for us it was a negative example. It means that we assume the label would say that the drive would stay healthy. Okay? So this was the main part that also improved the model. And all features, of course, computed with respect to a specific current date. This is to simulate in the best way a production environment in which you want to, run your model on a specific date, and you have only the samples that you got in until this day, and you cannot look into the future. So here are some results, and I would just say that this work is still in progress. For 14 days horizon, we got around, I think, 50% precision, a recall of 26%, which was much better than what we had before. It meant that we did manage to identify 26% of the failed drives. And what was most important for the business to optimize is the false positive rate, once again, because it's a much more expensive mistake. A false positive replacing a drive that would remain healthy, because this has the additional logistics cost, the new drive, and so on. Because of the limited time, I would just say that in a new version of the research, it's not only the modeling, but also another approach that we took in how to evaluate the model. we achieved the 50% recall with raising the false positive rate only to 0.5, and you can find all the details in our recently published CSTOR poster, which is available online. A word on implementation. The only challenge, the main or the only difficult thing from a platform perspective here was to compute all the time series features. It was done over a Greenplum database. It's a very powerful database that allows you to run native SQL. Native SQL in an efficient distributed manner. We use the PLR, if you know it, package. There was also a PLPy package that allows you to run R or Python aggregation functions, in our case, on your immediately on your database and get the time series-based feature really fast. And at the end, we got only one row per drive data set that we can use on a local machine and use scikit-learn for the modeling. Okay, almost no time to talk about current and other use cases, but there are many. We are working on overdrive prediction, how much time the drive will live past its stated time of wearing out, endurance modeling, flash failures, etc. Some key takeaways from this use case and other use case the team has experienced. Data science teams, at least in bigger corporations, or in many times, they should behave as educators for the value of data. You need to convince, and it's not always easy, that the data science is a must-have and not just a nice-to-have feature, as many executives today has in mind. A good way to do it is to do a POC over open data, which is similar to the data in question, and to showcase the potential using that. Always, of course, talk about your dollar value, whether it's a revenue generator or cost saving. This is the best way to convince executives in the need of your model. IT, once again, is captured as non-essential part of the data science lifecycle, but in many cases, IT has the data. It sits closest to the database, and you should see it as a collaborative and essential part of changing the data culture in your organization. In some cases, have in mind that you can at least be captured as a threat for traditional corporate analytics worlds, and this can give you some negative replies. So always come in a collaborative, non-aggressive approach. The real change must come top-down. It means that you have to work from the executive level. This is at least our experience shows. And always don't waste a good mistake. Learn from it. I hope you enjoyed. Thank you very, very much.